So thank you for this nice present introduction, and thank you ISGAN to host this webinar of today. So as stated before, the title of the webinar is IEC 61850 standard, so international standard, and the aim of this webinar is to address what is this standard for, which are the benefits for you if you want to develop a new project regarding smart grid and power substation and all the, let's say, equipment regarding smart grid and things like that. And what are the pending challenges for the development of these standards, and how the Osmose project, so European project, Osmose contributes to address these challenges. So just I will introduce briefly the Osmose project and the link with the IEC 61850 standards. And after I let the floor to Camille and to Christophe for introducing what is the standard for and what are the benefits. And at the end, we let the floor to Thomas to present what was done in Osmose regarding that. As an introduction, so Osmose project and the link with this standard is present in this slide. So Osmose project aims to address flexibility for power grid let's say, to manage variability and uncertainty in demand generation and grid over different time scales. So the aim of this presentation is not to describe how we will need more or new flexibility in the future for the power grid. But just as a sum up, the Osmose project works on it, and the proposed approach is to avoid silos approach and work on a holistic approach of flexibility. So why holistic approach? It's to address different kind of flexibility, from offer demand flexibility, so kind of not so fast flexibility, to system services, classical ones, and to dynamic grid management, thanks to different sources of flexibility that could be coupled, as demand side management in factory or in residential sectors, as renewable energy management, grid management, or the use of storage. So one solution could help to address all the type of new flexibility we need, or we can combine in a hybrid solution different source of flexibilities to address different services of flexibility. So Osmose project is a European project started in 2018, and it will finish in 2022. It is managed by French TSO RTE, and there are 33 partners from 9 countries, among them several TSO, several industrials, and also research centers. Osmose project is structured in 2 main packages, let's say. The first one is on method and simulation, with a working package on that try to identify cost optimal mix of flexibility for the European power system, taking into account all the foreseen change in this European grid regarding renewables or new electricity needs. Other working package work on robust improvement of market mechanism and regulations serving this new kind of flexibility identified. And the other, let's say, big package is on demonstration of these flexibilities. So first, demonstrators is managed by RTE and is a hybrid system serving different kind of flexibilities, among them grid forming capabilities. Second, demonstrators is also a hybrid system, but more dedicated to multi-services for, let's say, weaker grid, electrical grids. The third, demonstrators is multi-site demonstrators that consider renewable management, demand side management, but also dynamic grid management to deserve different kind of flexibility. And the last one work on a cross-border exchange of flexibility through dedicated market close to real time. The last work package is the one that integrates our discussion of today. Is not a scaling up and replication task, but more the development of tool to help scaling up of and replication of the demonstration studied in Osmose. So in this last task, let's say there are three main tasks. One is on battery energy storage system design and control. So design what are the optimal size. With also a focus on database and data analytical tools to assess the performance and the aging of battery storage system. One task is on TSO-DSO flexibility coordination. So how to activate flexibility on DSO grids, taking into account TSO constraints. And the last one is on interoperability, so the topic of today, and it works on IEC61850 interoperability framework. It aims to demonstrate the engineering process of the standards profile, so with different specification tools. So a standard, a profile is made of a data model and an engineering process on the communication and of information between different electronic device of different vendors, it could be. And the last aim is to demonstrate this interoperability framework offered by IEC61850 standard with products of different manufacturers. So I will let the floor to Christophe and to Camille to explain you better in depth the standard. And if you have question, you can use the question and answer ISGAN tool. And if you have more question on Osmose project, you can go to the website.
Thank you, Yves-Marie. So this part will be the introduction of 61850. This will be really a short introduction because we can pass many and many hours to explain what is IEC61850. So this part will be presented by Christophe Brunner and myself, Camille Bloch. I will present you where and how IEC61850 is used, and Christophe will present you IEC61850 used for distributed energy resources. First of all, as a reminder, here is what we are calling a smart grid. It covers the whole area of energy management from supply side down to the demand side. So it covers production, either centralized or decentralized bulk or renewable energies. And this is what we are calling the field. Then, purpose of the smart grid is not only to describe the field level, but it also addresses the information management level. And this information management level is in fact the activity on top of the field which intends to operate the grid properly. It covers the transmission, the distribution, the customer management, and also services. And to have what we are calling a smart grid, we need to have efficient and reliable information exchange between all these actors. And on top of that, there is also the energy market, which requires to gather information from all parties. And IEC61850 is one key standard in the smart grid as it addresses interoperability for operation of the smart grid. As of today, IEC61850 applies to the following area in gray. It covers production, transmission, and distribution. And at the boundary with grid users, there are meters which are becoming more and more IEC61850. But IEC61850 is a standard which is not limited to smart grid. It is already used for different domains which require an efficient energy management, like oil and gas, mining, transports, and data centers. And so IEC61850 intends to standardize exchanges between the different parties of the smart grid. First level of standardization is the data semantic. Instead of giving a number or user-defined text to identify a data in the system, IEC61850 has already defined a dictionary of data types. For example, a commonly used circuit breaker have some management function. And so a circuit breaker management function is identified in IEC61850 dictionary by the term XCBR. And a position of any switching device is identified by the word pause. So any device identifying a position of circuit breaker using this representation, so it will be xcbr.pause, will be self-descriptive for any interacting device. Then, a second level of standardization is the engineering process. A standardized configuration language has been defined. It's called SCL for System Configuration Language. This allows to describe the configuration of a device participating to data exchange in interoperable way using a dedicated file, allowing other devices from different manufacturers to understand it. And then an engineering process is based on these files with dedicated tools from system and device engineering. And the last level of standardization is the communication based on different communication protocols, depending on the kind of data exchange which is required with different level of performance. If you want to archive your data, the different status of your data, then you will not need to have a really efficient communication protocol. But when you want to do some protection algorithms, then you need more performant communication. And you can see here that we often call 61850 as standard protocol, but it's more than only a protocol. It is really composed of all these three pillars. Then IEC61850 scope is already large and is still growing. In this picture, you can see a summary of current and future scope of IEC61850. First target for the standard was power utilities, addressed in the first edition of the standard in 2003. And it grows to include different aspects of energy management system. First, it has included engineering of communication network for local or for wide area network. And recently, it also has included deterministic networking technology to have a more reliable communication network. It also covers communication outside the substation, for example, to other substation or to control centers. And also to finalize with the communication aspect, it offers mappings to all commonly used standards like T101, T104, DNP3, and Modbus. And these commonly used standard protocol mapping are used to include to make the reach to existing systems. A second target was to address other domains as substation. Now, IEC61850 integrate distributed energy resources like hydropower plant, wind and photovoltaic farms, but also electrical vehicle charging station or storage systems. And finally, IEC61850 is integrating extending function in energy management system. For example, it has been integrated specific data modeling for grid scheduling or for condition monitoring. This allow external application, so not application directly related to electrical system management, to interact more easily with an IEC61850 to gather data from the field directly and do some analytics or some scheduling in the future. And we also have ongoing works, so shown here with a dotted line in blue, to add new kind of protection, for example, with the traveling wave fault, or new features like system management. IEC61850 is bridging old system to new fully digitalized system, and we will see in coming slides two major evolutions from old legacy standards. So first evolution was to define one unique standard to cover power system. Here, this is an example of a power system which is based on three major layers, which have to interact together. From the top, we have the station control with human interface or gateway features, which have to interact with many devices at the bay level, and these many devices which control the electrical process by interacting with the electrical equipment. In the past, with legacy protocol, so the old protocols which are already existing and used in many projects, there was many standards and protocols defined for the communication at station level. And for communication at process level, there was no really standard defined, mainly proprietary communication based on the manufacturer requirements. And all these standards are depending often on the domain, the region, or the manufacturer which have to implement it. This approach has led to an inefficient system engineering with many adaptations to be supported, many protocols to be managed by the station control, and risk of incompatibilities between devices. And this also increases the cost of maintenance to the different risks which are not well managed. Then with IEC61850, the objective was to have one common standard for the three different levels of the power system, capable to address communication between the station control, the bay level, and the electrical process, with at least the same level of performance, and in some cases, a higher level. So this has increased the interoperability between the different devices, allowing users to build heterogeneous system when in the past it was preferred to have a system owned by only one vendor to reduce the risk of interoperability issue. And IEC61850 has brought another brick on top of that, which was a common semantic in an electronic format, allowing machine-to-machine exchanges with less risk of misinterpreting data between different devices. This allows so to increase efficiency in the system setup by using one common interface and reducing risk and cost of deployment and maintenance phases of the system. Then second major evolution was to improve the engineering of power system. In the past, with legacy protocol, there was not really well-defined common engineering process, and it was based more on the knowledge of system integrators on how to work with the different kind of devices. The knowledge was spread in different non-machine processable files, like Word document for the user requirements, product data sheets provided by each manufacturer in its own format to know the capability of the device. And the user or the system integrator was in charge of defining a big data sheet, often called data list, to describe the data required by the system and the exchanges to be configured between devices. Then these data exchanges descriptions were entered manually in each device's configuration tool with a specific representation not harmonized between vendors. This brings then a high risk of human error, a system incoherency when the data was not correctly entered at one level of the process, increasing the commissioning time and risks. And then also the maintenance with a less error-prone system. And to address these problems, IEC61850 put in place a standardized power system engineering process. As explained earlier, the configuration is now described with a standardized language, the SCL, using a set of standardized machine processable files related to the role of the file in the process, like the SCD file, which is a complete system description, or the ICD file, which is a product data sheet of a device. This language is describing only interoperable elements of the system, not private stuff of each devices, like protection algorithm or internal data management. The configuration files will contain the description of electrical system with the electrical equipment and functions used to manage them, like protection, control, supervision, and monitoring functions. The configuration files will also contain the description of the devices with the data model of the function handled by them, using the semantic model defined earlier. And finally, the configuration file will contain the communication configuration of the devices and the data exchange between them. So all the interoperability point of your system will be described using one kind of file, and the complete description of your system will be handled by the SCD file. Then these files are under responsibility of different tools with standardized roles capable of integrating SCL files provided by other tools. And one main tool called System Configuration Tool, this big one, is responsible of the engineering and coherency of the whole system, which will be automatically integrated in the manufacturer configuration tool here, without any need of re-engineering the communication by a human. This approach is reducing risk of human errors and increase efficiency of the system engineering. Now, I will leave the floor to Christophe, who will present you this concept applied to distributed energy resources.
Okay, welcome everybody as well now from my side. I hope you can see my screen. As Gami has introduced a little bit the concepts of 61850, I will now try to explain you how IEC61850 is applied to DRs. As you know, when we talk about smart grids, managing of the information in a smart grid environment is a key element, because there is a lot of information that has to be handled. Having such information available in a standardized semantic model definitely simplifies the integration, makes the integration easier. So that's why the key focus of 61850 applied here to DRs is on the data model. So before I go into the details of the DR modeling, I want therefore to go a little bit in more details about the elements of a data model in IEC61850. So what is the concept behind IEC61850 with regards to information management and information exchange? The IEC61850 standard talks about ID, or intelligent electronic devices, which are the typical equipments that we have in a power system. IDs are not standardized, but every ID has, depending on its functionality, a data model with information that we can access from an outside world. And that's where IEC61850 starts, by defining standardizing such a semantic model based on the functionality. And this is done in the parts 7.4 and 7.3 of the standard. We are mainly talking here about logical nodes, which are functional elements representing a certain functionality, and they contain all the information that we may exchange associated to that function. Once this information is defined, in order to have interoperability in a standardized environment, we also need to know how we can access the information. And this is done in another part of IEC61850, which is the part 7.2, which describes the generic aspects of information exchange. 61850 supports multiple communication principles, can be event-driven, but it can also be requested, and we can get the value back. We will not focus too much on that. Our key focus here is really the IEC61850 data model and how that applies to the DRs. So this gives an example of such a data model. A data model is hierarchically structured in a device, and depending on the function supported, we will find various elements. In the example here, we have a device that has a protection part, where we have some protection logical nodes, like a PDIS, which will be a distance element. We also have a control part, and in this control part, we have, as an example, a model of a circuit breaker, which is called a logical node, and this logical node in this case is called XCBR. That's one of the elements of the standardized data model, and it's then further defined that such a logical node XCBR contains a data object called POS, and that's where we find the position of the breaker. In particular, we find the position at the data attribute stval or status value. So that's the concept of the data model in IEC61850. So IEC61850 in the standard parts related to data models define a lot of these so-called logical nodes. We have here a few examples of such logical nodes as we may find them in a substation. As Gami has mentioned, that was the first scope of application for 61850. The substation automation system. So we find here logical nodes like, as an example, XCBR representing the circuit breaker as an equipment with all the information that we can gather from that equipment defined as a standardized model. We have other elements like current transformers, switches, like disconnecting switches or earthing switches. But in a gas insulated substation, we also may need to measure the insulation media, the gas density of the insulation media. 61850 has also a model for that. The models that we have seen here are all related to physical equipment. So they model the information that we get at an interface from the physical equipment. But of course, in a smart grid system or in a substation automation system, we also have application functions that produce data. So there's more logical nodes available, like we see here. We have protection elements like PTOC, overcurrent protection, distance protection. We have measurements, control functions, switch control functions. So there's a lot of logical nodes defined in the standards of 61850. When we are now talking about DRs and 61850, there is one dedicated part, which is the part 7-420, dealing with everything that is required to model a DR, a distributed energy resource. And that's what we want to have a look now in more details. First of all, when we talk about DR and DR integration into the power system, there's a couple of typical aspects of such a DR that need to be considered when we talk about the data model. First of all, a DR can be a generator, it can be an energy storage, it can also be a load, it can also be combinations of that when we are talking about a larger system. From a utility perspective, as a utility is responsible for the reliability and the electrical requirements within a distribution or transmission system, they may also need to be able at least to deal with DRs that are connected to the distribution grid. They need to be able to deal with a large amount of DRs that may be connected. So a utility may need information about where the DR is located, where and how it is connected to the grid, what are the capabilities of the DR, which grid codes, as an example, are supported. It may need to be able to parameterize these grid codes. The DRs definitely have to comply with grid codes. And the DR can also assist the utility in meeting utility requirements, as we can, as an example, use controllable loads that helps us to do peak management. And there is various applications where DRs can also support the utility to meet the requirements. But it's not only the utility that has to interact with a DR. There is also other entities that may interact with a DR. On its most simple way, a DR is working autonomously, controlled by a DR controller, producing the energy or whatever it is supposed to do. But we may also have, on larger sites, multiple DRs grouped together, may be operated by a facility DR management system. We may have third parties that interact with one DR or with a system consisting of multiple DRs at distributed locations. As an example, creating a virtual power plant out of multiple DRs by an aggregator. The aggregator needs to be able to interact with the DR in order to control it to fulfill its requirements. And as already mentioned, last but not least, also the utility needs to be able to interact with the DR, typically in emergency situations. When we have problems in the network, there may be a requirement from a utility to interact as well with a DR. So to enable the access of these different stakeholders to a DR, I think it's very important to have a standardized semantic data model, which significantly reduces the integration effort when you know exactly what you can get as an information from a generator, instead of when you have to engineer each and every system with its particular information exchange. This is a few examples of typical information we need from a DR. We may need the nameplate information, like capabilities of the DRs, ratings. An aggregator that uses the DR needs to know what is the maximum power capacity that can be produced, as an example. He may also need to know, is it intermittent? Is it a photovoltaic or something else that is more intermittent, not necessarily guaranteed? Or is it something that produces always the requested energy? Operational settings need to be exchanged, on one side for production, but maybe also for grid code functions. We may need to be able to influence the settings there, certain settings required from the grid codes. Real-time data, like the actual power output that is fed into the network, may be required to be exchanged. We may activate certain operational functions. A DR may support volt-var control, as an example. We may need to activate this support if we want it to do that. If you are just using a DR with active power, we may want to send schedules instead of individual set points to the DR. So this is all kind of possible information that we have to exchange with a DR, and which is the scope of the data model that we build up with 61850. The fact that we have often DRs grouped together in DR systems, this is addressed in 61850 by providing or supporting a hierarchical modeling concept. So the 61850 model for a DR on one side allows us to model a DR unit, but we can also model a DR system as one entity from a next higher hierarchical perspective, which can be a mixed combination, as an example of a photovoltaic system combined with a storage device. We may model that as one DR system to the outside world that can then be looked into from an aggregator, can be used by an aggregator, or can also be used by utility. And in principle, we can have multiple hierarchies, and somewhere we have a top level DR. We can also look at that as a total. So that's one of the aspects that is supported by the 61850 model for DRs. The DR model, as we define it in 61850, the part 7420, consists of 4 main components. It's quite a large model, having multiple aspects. These 4 main elements include the modeling of what we call the resource itself. That's the main focus of today's presentation, the resource, which is looked at in from an abstract perspective as a generator, a load, or a storage. It also may include a power management function. It may include operational functions. Operational functions are the modeling of the various grid codes that are supported, as an example, by the DR. If a DR supports volt-var management, as I explained before, there is a dedicated element in the 61850 model, which is in that case a dedicated logical node that is modeling the characteristics of this volt-var behavior of the DR resource. Last but not least, we also have to model what we call the electrical reference point, which is modeling where the DR is connected to the grid. It's modeling how it is connected, if it's a single phase connection, a 3-phase connection, and some other aspects. When we look a little bit more in the details of the resource modeling, the aspect of the DR resource, IEC61850 has introduced 3 logical nodes for that purpose, which are generic logical nodes. One is the generic generator, the other one is a generic load, and the next one is a generic storage entity. So depending on what kind of distributed energy resource we are using, when it's a generator, we will find a logical node dgen, where we model all the information that you need or you expect to get from a generator, independent of its technology behind. What we typically find in this logical node is the aspects of the electrical resource, which could also be aggregated, like capabilities, ratings, but also settings, the status, is it active or not? And as mentioned, such a generic DR resource can be a generator, can be a load, can be a storage. If you are talking about a DR system, which is hierarchically combined, it can also be a combination of multiple of them. If the DR resource that we are modeling is a single DR, then we also have a technology-specific logical node associated, where we find the technology-specific information. This is shown on the next slide here. So this is a little example of a model of a photovoltaic system as a 61850 DR resource. So we basically have a first logical node dgen, which is the generic generator. That's where we find all the generator characteristics of our photovoltaic installation. But then we have associated to that a specific logical node, which models the photovoltaic array or system as such. That's where we find all the information specific to the photovoltaic device. IEC61850 also supports, as I mentioned, the modeling of a storage system. A storage system, as we all know, can either be looked up as a generator when the storage system is feeding energy into the grid. It is a generator, so we have a logical node dgen, which is modeling the generator specific information of the storage system, but it also can be a controllable load. So we have also a generic logical node DLOD available, which is modeling the load characteristics like active power, rated active power that it can consume. And as it's also a storage system, we also have a generic logical node DSTO for modeling the generic storage aspects. That's where we typically have the maximum capacity that we can store, but there we will also find the actual state of charge of the storage system. So we have basically, when we model a storage element, we have these three generic logical nodes together, and then we may have a dedicated logical node when we have a battery as a storage system where we find the specific information related to the battery. Okay, so that was a short overview on the aspects of 61850 for DRs. So basically, the key contribution of 61850 here is that 61850 defines the complete semantic data model of a distributed energy resource. So it decomposes all the information that we can get from a distributed energy resource unit or system. It decomposes that in these various elements, modeling on one side the generic capabilities that we expected from a generator or from a storage or from a load, but also specific information that may be needed for maintenance, like for a battery, maybe information like how many cycles have been done, when do we need to do a recycle to maintain the life of a battery. That is also available. Also, in the 61850 model for DR, we can describe and model all the grid codes that are supported by the DR as dedicated logical nodes for operational functions. If a DR supports voltage write-through, we can describe the parameters of this voltage write-through in a standardized way. And last but not least, what 61850 as well supports, mainly for integration of devices with legacy interfaces like a Modbus or a 104 device, IEC61850 also defines some mapping parts that allow us to link information elements from a legacy protocol to the Semantic 61850 data model. As an example, if you have a Modbus device, a Modbus interface to your DR system, you can describe, based on some parts of 61850, in that case this is a 80-5, you can describe what a dedicated point in the Modbus information model refers to in the 61850 world. So you can describe where in the Modbus interface you may find information like the currently produced active power and so on. And with that, I think the next part of the presentation will be Thomas, that is now talking about work performed in Osmose, or are we answering questions in the middle? I'm not sure anymore.
No, we are answering questions at the end, Christoph. Thank you.
Okay.
Thank you for the introduction. I will now share my screen. Okay, so good afternoon, everyone. My name is Thomas Sterks. I work for Elia now for almost 7 years. I work at the expertise engineering secondary systems department, where I am involved in everything what is related to 61850, implementation of a digital substation and linked engineering processes. And in this part, I will try to show you the link between the Osmose project and the 61850 standard, and how within Osmose we are trying to contribute to this standard. So within task work package 7, there is a specific work package 7.1 that is speaking about interoperability. And perhaps as an introduction, when we speak about interoperability linked to 61850, a lot of people only think about interoperability between the devices of different manufacturers. But actually there are a lot more aspects to that. And as explained Camille already, for example, there's also interoperability between the different engineering tools and between the different process steps of your engineering process, for example. And what we're trying to do within Osmose is to work on most of these points, but specifically, and this is the first point on the left, specifically on the engineering process, based, as already explained by Camille, on SCL, so the system configuration language, and trying to support a process top down from concept to execution. So trying to transfer all steps of an engineering process to 61850, trying to support that completely. It does not remain a technical or a theoretical exercise. We are also demonstrating the process in a multi-vendor setup. So multi-vendor does not only mean devices from different manufacturers, but also softwares from different software manufacturers. So it's really a multi-vendor setup on multiple levels. We are doing this in a laboratory environment at R&D Nestor in Lisbon, where we are simulating 2 substations which are interconnected and that each contain a battery storage bay. So we work on the process, we demonstrate it, and as a result, we will provide recommendations to the 650 Working Group 10 in order to improve the standard on multiple levels. So first of all, the engineering process, but also we will communicate any data modeling gaps that we detected during the modeling of our exercise of the demonstrator. And we do not only provide feedback to the standard, we are also organizing the communication of our results to the market by, for example, organizing this webinar, but also by giving presentations on conferences, publishing papers, etc. So we are also working on speeding up the integration of our project here, the results of our project into the market. So these are the 4 main topics on which we work within Osmose. And by we, I mean representatives of all the domains of the market. So not only utilities. So from a utility side, we have Elia, Red Electrica, and REN. There are also ID manufacturers involved, like Siemens, FASEC, and Ingeteam, software vendors that provide us with the necessary configuration and specification tools like Helix and Schneider. And within our team, we have a lot of people that are deeply involved with the 61850 standard, like, for example, Camille and Christophe, which are present here in this webinar. So just to show you that we are a big team and we have representatives from all the domains of the market. So this is not something that is pushed by only one party of the market. This is really a common work between all partners of the market. Now let's dig a little deeper into the first point related to the engineering process. On the left, you see an image from the 61850 standard explaining the exchange of files between the different tools and between the different environments. And the part that we are focusing on is the top part, which is related to the specification, to the system specification. What we are doing within Osmose package 7.1 is trying to provide the necessary extensions to extend this step in order to have the ability to create vendor-independent specifications and allow in the process to make machine-readable specifications. As I said, vendor-independent, but also to define data flow within this specification, which was not yet possible in the past. We are not only providing the SCL extensions, we are also providing the tools to demonstrate this process. So the participants of the project are extending or developing tools in order to support what we are defining. So we have now tools that allow creating functions and subfunctions for a specification. So in a vendor-independent way to really specify, let the user specify what he wants, how he wants the system to communicate and behave, independent from what any device can do. Tools which allow also to create links between these subfunctions, so to create the exchange of data between subfunctions, again in a way that these subfunctions are not yet linked to any device, so completely in a device independent way. And we are also providing the necessary extensions to, in a later stage, then map the real IED data model to what is specified, but in a way that we do not lose our original specification in the files that are used in the next step of the process. So it means that we can, in all stages of the process, retrace back what we originally specified. So at the bottom, you see a basic representation of the process, and the first steps are the ones on which we focus within Osmose. So on the left, you see the definition of functions and subfunction templates. Then you will combine these into your specification. So in what we call a system specification tool, where you combine the concept of functions and subfunctions and create data flow between them. You optionally have the opportunity to allocate IEDs to it if you want to. It's not mandatory. You can create a completely independent specification, independent from any physical allocation, but it's optional. And then in the third step, you can merge what you specify with what you get back from an IED manufacturer, for example. And the IED manufacturer provides you files directly based on what your original specification was. And so why is this important, all this work? Because it's important because it improves the overall engineering process efficiency by extending the process not only from configuration and installation, extending it with everything that's related to concept and specification. It allows a user to provide machine-readable specifications to the market, and in this way avoids any interpretation errors from any manufacturer. So by providing machine-readable specifications, you improve your efficiency because you can recover the work already done and you avoid any interpretation errors. And as a third point, as I already said, it allows also tracing your concept and specification through all the steps of your process, which helps you in improving your version management because you can trace the version of your concept that you use in all steps of your process. So up to the execution point, you still have the trace back of which version of your specification that was used. And as a second advantage of the traceability, it allows you to create a way to enable automation in updating these files. Because you still have your original specification in the file, tools may be able to update these files with new versions of your specification. So as a conclusion, there are a lot of possibilities with the work that we are doing here, a lot of advantages in improving your global engineering process efficiency. Then the second point related to the demonstrator. So our engineering process is not only a theoretical exercise, we are also demonstrating it at the lab of R&D Nestor with multi-vendor hardware from Siemens, EFASEC and Inge team, engineered with multiple tools, tools from Helinx, Schneider, but also system configuration tools from the vendors, from the IED manufacturers. In the lab, there's also a possibility to simulate the behavior of the grid. So we can really extensively test the demonstrator there because we have all the necessary equipment available. And on the bottom, on the left, you see the configuration that we are demonstrating here. So an interconnection bay in 2 different substations, simulating a high voltage interconnection line between those substations, with on each substation a storage bay which is linked. Then the result of all this work will be documented into recommendations for the 61850 standard based on 2 main messages. First one is related to the improvement of the engineering process by communicating all the SEL namespace extensions that we defined, by providing recommendations for the content of the different SEL files that are used within the different engineering steps, and also by providing recommendations for engineering tools, for what should a tool be able to do in order to support fully this process, for example. And as a second recommendation, trying to improve the data model, because from this execution of the demonstrator, we have detected some gaps in the standard related to the data model. These are also recommendations that we can make to the 61850 standard. As a last point, dissemination of our work. So this slide is providing a list of what we already did and what is also upcoming. So we communicated already in the past at the 61850 Global Conference. There's an interesting article in the PacWorld edition of December 2020. And there's also already the first deliverable of our work available on the Osmose website, where, for example, we compare a classical engineering process with the engineering process that we have developed here. So it's really an interesting document, which is shared with you via the Osmose website. There are also some additional upcoming webinars. So there is the webinar together with EU-SysFlex project on TSO-DSO interaction, which is on the 16th of June. There will be a second webinar linked to this one, where we go more into detail about what we are doing and the results that we have from our work. It will be planned in Q3 normally of this year. And we will also be at the 61850 Global Conference of this year in October, where we will also present the results of our work. Okay, so this was the part related to the link between Osmose and the 61850 standard. As a last point, we will jump to the conclusion. So 61850 standard enables interoperability between many things. First of all, the information management levels like TSO, DSO, but also from the process part of a substation to the station part of a substation. It enables also interoperability between the different steps of the engineering process and the tools that are used within each step. And of course, also the interoperability between the devices of different manufacturers. And what we try to do within the Osmose project helps pushing forward the standard on multiple levels, and specifically the level of the engineering process, trying to provide the necessary extensions to make the global engineering process more efficient, and then specifically at the specification part. And we also provide the necessary recommendations related to the data model exercise that we did within the demonstrator that we use within Osmose. This was the last slide. Thank you for your attention. On this last slide, you see the names of the presenters, and perhaps I can give the word back